OK, parfait.
And so I use simplicity very often as a strategy. Keep simplifying the problem actually fairly ruthlessly till it's minimal, till it's the simplest problem that contains the nugget of the difficulty, the essential difficulty. And that's actually my taste in math. Different people have different tastes, but my own taste is I like to do the simplest thing that contains the essential difficulty.
Welcome to the Night Science Podcast,
where we explore the untold story of the scientific creative process.
We are your hosts.
I'm Itai Yanai.
And I am Martin Lurcher. Today we have with us Stephen Strogatz. Steve is a professor of applied mathematics at Cornell University, where he has been for nearly 30 years. Prior to that, he studied and worked in Princeton, Harvard, Boston University, and MIT. Steve has very broad research interests. Early in his career, he worked on many problems in mathematical biology, including the geometry of supercoiled DNA, the dynamics of the human sleep-wake cycle, the topology of three-dimensional chemical waves, and the collective behavior of biological oscillators, such as swarms of synchronously flashing fireflies. His most recent book, Infinite Powers, is about the origins and modern applications of calculus. It has become a New York Times bestseller, and it's a pure joy to read. We truly recommend reading it.
And in 1998, Steve wrote a paper together with his former student, Duncan Watts, on networks with what they called a small world property, where there's both tightly knit interactions, as well as this uncanny ability to get to anyone in the network in just a few steps. This paper was published in Nature, and it's widely regarded as a super important contribution to the interdisciplinary field of complex networks. It's been cited 45,000 times at least, and it's inspired many of us, including Martin and I, working in the field of network biology. Steve Strogatz is a fellow of, it seems, every notable science organization in the US. If he's not a fellow, it says more about the organization than it says about Steve. And from a US perspective, just as we have a national poet, we should have a national mathematician, and then it would have to be Steve. So Steve, we're so happy that you're with us today. Welcome.
Well, that is incredibly kind, Itai and Martin. Thank you. If you could somehow hear a smile, maybe you can hear it.
Yeah.
That's really something. National mathematician. That's a very charming thought. Thank you.
We hope that we've sparked this idea and that it will take flight and
become reality. Yeah,
exactly.
Yeah. Well, welcome to the Night Science Podcast.
Thank you. Thank you so much.
When we just chatted before we started the recording, we talked about how the term night science is borrowed from the autobiography of Francois Jacob. And you said that you have some relation with Jacob?
I do. I never met him, but when I was in college, in my senior year, we had a required senior thesis. Everyone had to do a research project. I asked a mathematician in our department, the closest thing we had to an applied mathematician, to suggest something that would combine math with biology, which I was interested in. And he said, well, there are nice problems about geometry of DNA, especially when the double helix itself gets twisted to form a so-called superhelix, so that you have supercoiled DNA. But some other friends of mine said, well, you have a chance to talk to one of the world's great experts on this. There's a biochemist here, which was actually the term that people used to use before molecular biology. I mean, he was in a department of biochemistry, a gentleman named Abraham Worcel, Worcel. So Abe Worcel was a great expert on supercoiling, and I went to talk to him. And when we were trying to work out something called the higher order structure of chromatin, at some point he started telling me about Francois Jacob, who was his postdoc advisor. I think they worked at the Pasteur Institute together. DNA, double helix, that's something we all learn about. The next level of structure above that in eukaryotic organisms would be to take the DNA and wind it around proteins called histones in a structure called the nucleosome, which was only discovered around 1974. And so at the time I was working, this was 1979. So the nucleosome was still a very new thing. And so there was this picture of DNA wound around these nucleosomes like beads on a string. or I should say like string on beads. But then there came to be the question, what would happen next? I mean, how do you take the beads and string and further compact those en route to getting a full chromosome? So that's what people meant by the higher order structure of chromatin, chromatin being this mixture of protein and DNA. And so anyway, Warcel had an idea for what the next level of compaction was above the nucleosome. And he made a little model with ping pong balls for the nucleosomes and rubber tubing like you would see in any laboratory.
No
for
way.
the yeah. You can see photographs of it. It's in my first published paper. We ended up doing some work together that got published in Proceedings of the National Academy of Sciences, which was really thrilling. Yeah, I have my first paper in PNAS as an undergrad. It was insane. But so it used to take this crazy looking ping pong balls with rubber tubing stapled onto them and then wind it up to make what he thought was the higher order structure. And he would say, this is what Jacob used to tell him to do, to think about structures by actually putting them in his hand, making a model, twisting them, feeling their elasticity, feeling their resistances, and which grooves were more or less compliant to bending or twisting. Anyway, so yeah, I always felt like Francois Jacob was kind of lurking in the background with his love of symmetry and beauty, not usually traditional things to emphasize in biology where there's so much, talk about diversity and accidents of natural selection and stuff. But Jacob used order and beauty as a kind of guide. It wasn't a certain guide, but it was a guide.
That's really interesting, what you said about beauty, because when we talk about nature, then beauty is often something that we think about, but not so much in a scientific context. So in your mind, what is the role of beauty in the sciences?
It's so complicated. It can be a guide that is reliable or unreliable, depending on any given problem. So in physics, especially theoretical physics, there are great proponents of beauty. Einstein was one, Hermann Weyl, Paul Dirac. There are many great theoretical physicists who used elegance of equations, by that meaning something like minimalism, no unnecessary terms, the smallest set of terms in a governing equation that would account for the phenomena of interest. That has often been a decent guide, or sometimes an uncannily good guide to what the correct laws of physics are. But I think in biology, there's a tendency to feel that, certainly there are some examples of beautiful structures. I'm thinking of shapes of diatoms or, other things that are almost like physics that become life. But on the whole, I think the lesson in biology is often that there's evolution and things happen in the distant past that then get baked in and are carried along genetically. And so they might not seem beautiful anymore. For instance, I'm told that our retinas are installed backwards.
Oh, okay.
That the photoreceptors are sort of like you wouldn't design
That's
things.
why you have a blind spot.
Yeah, right. So you wouldn't design the eye. If you were trying for the most elegant design, you wouldn't have come up with what we have. And there are countless examples like this. So,
but as a mathematician, Steve, do you think that mathematicians do use beauty as a kind of true north to give intuition? You say that it's sometimes unreliable, but don't mathematicians still take a chance on it?
Sure. Well, that's right. So, we don't have a concept of evolution in math. Obviously, there's evolution of ideas over historical time because math is built by people. But the subject itself has a timelessness to it. There is no time dependence in geometry or algebra or anything else. So their beauty is a very good, powerful criterion. And absolutely mathematicians, probably more than just about any other kind of scientists, absolutely use beauty as an important criterion, maybe the most important, that we're constantly talking about elegance, beauty. It's a little unclear what we mean by that, but...
when you mentioned evolution, I didn't think initially that what you meant was some kind of force that messes things up, but rather as an organizing principle, a very strong underlying force. And that's interesting to think that maybe in math, that organizing principle is beauty.
It could be. Yes, maybe it is. Our number one principle is logic, right? Things have to be true.
Things have to add up.
Things have to add up. They have to be true. True, of course, now we're getting into, such murky philosophical waters here. Right, this is night science, isn't it? We like to tell ourselves that we start from axioms, and the truth status of axioms is ambiguous. There's no, like, the axioms aren't true or
Yes.
false. The axioms are just assumptions.
Mm-hmm.
And then from there, we use logic to try to deduce true consequences. At that point, you can speak of truth. Does something follow from something else or not? But the original axioms, there's no notion of truth associated with them. Anyway, you can have axioms that are more or less fertile as opposed to beauty. I mean, fertility is another concept. How rich of a theory develops out of, let's say, assuming that Euclid's parallel postulate is true. That's the statement that if I have a line and then a point that's not on that line in a plane, that there's exactly one line that goes through that point that's parallel to the other line. That's a property that's true in ordinary flat geometry, Euclidean geometry of the plane. But in non-Euclidean geometries, so-called hyperbolic or spherical geometry, that axiom is dispensed with in favor of other axioms. There might be no parallel lines, or there might be infinitely many parallel lines.
Right.
And those are perfectly good geometries. They're logically as good as Euclidean geometry, and sometimes they're more important scientifically. Like, we think for doing cosmology and astronomy, we need curved space geometries, especially, like, say, near a black hole or something like that. So anyway, I feel like, yes, beauty is an important criterion in math, the richness of a theory that arises. Another thing we care about is connectivity. I would say an aesthetic high point in math, if we're going to talk about beauty, is when one part of math connects to another in unexpected ways. We really love that.
So you're telling us that one way to perceive beauty in mathematics is this connection between different mathematical disciplines. But more generally, what is beauty? Are there other aspects of beauty that are obvious to mathematicians?
It's a very hard question. The things that people often bring up are economy, so no unnecessary parts. Economy of means, simplicity is closely associated with beauty for some people. Not everyone, but like when you do popularity contests of what is the most beautiful equation, they do this, right? They have this every so often. There's what is the most beautiful equation, and
A lot of top 10 books.
yeah, people love those kind of things. And almost invariably, the winner is an equation due to Euler.
Right.
That if I say it, maybe you want to say it out loud? You know the one I mean?
Is it e to the power I pi plus 1 equals 0?
Yeah, that one. Exactly. That is almost invariably the winner. And so you could ask, since I like to be concrete about these things, what is it that makes us want to say that is a beautiful equation?
Well, it's like every cool number or symbol all in one equation. It's crazy.
Exactly. That's right. So you have e, I, pi, 1, and 0. Those are some of the most important numbers in math for all kinds of reasons. And each one is a kind of emblem of a larger body of ideas. Like 0 is sort of the void or the vacuum, nothingness. 1 is the beginning of counting and arithmetic. Pi is attached to geometry and circles and curves. And E is a mascot of calculus. And it has to do with exponential growth and decay. And I is sort of like algebra, that numbers don't have to just mean magnitudes. There's a more general concept of a number-like object that we used to call imaginary. We still do, but it behaves in many ways like an ordinary number. So anyway, all of these things are packed into this one equation.
But really, that means that here it's again what you said before, right? It's this connection between different mathematical disciplines in one equation that people find beautiful, right?
That's one aspect of the beauty of this equation. It's connecting 5 disciplines. There's more, right? Because it combines the basic operations of math. It has a plus sign. It has a multiplication, I times pi. It has exponentiation, e to the I pi. It has everything in the shortest possible space. And best of all, so it's not just that it has all the connections, which it does, but it also has an element of shock. It's completely shocking, first of all, that you could think of raising a number to an imaginary power. What the heck could that mean? And that this equation could actually be true. It's got everything in the tightest possible space.
So I agree with you that it's got an economy, but would you call it simple?
Well, not exactly. Right. Yes and no, that's a problem.
It's beautiful, but it's very confusing. Very few people can say they get it.
True. It's right. So you might view that as a negative or a downside of this equation, that you need a certain amount of advanced knowledge to be able to perceive the beauty here, which is not so surprising. There are many things like that in life. For instance, opera. People who love opera will start weeping. But it's true, right?
Right.
And if you
Right.
you don't know opera, it seems kind of like, oh, come on, what's all this shouting and carrying on and
So much drama.
yeah, get over yourself.
But if you do get it,
It's so moving.
What about symmetry? Is that something important for mathematicians?
Yes, definitely. Symmetry is another good criterion. And that's one that Jacob used to emphasize a lot in his biological examples. That was something that Warcel highlighted for me back in my undergraduate days. But yes, mathematicians love symmetry. Symmetry being defined as, roughly speaking, a property of an object such that when you make a change, it doesn't cause a change. In other words, draw a circle on a piece of paper. Now rotate the circle around its center. Well, it still looks like the same circle. You can't see any change, even though you made a change. You made a rotation, but it didn't have any effect. So that's because a circle is rotationally symmetric. Same thing with a face that's bilaterally symmetric. Not that any of our faces really are, but let's say a Rorschach pattern. If you flip it across its midline, it's then the same shape. So anyway, yeah, symmetry is a kind of simplicity, right? Because it shows changes that don't cause a change.
So we've talked about the elements of beauty from a math perspective. It's simplicity, economy, symmetry. And, what Martin and I are thinking about a lot is the process of science, the process of math. How is it that we come up with ideas? And so what is the process of beauty for providing this kind of intuition? How do you use that to guide your work?
Well, for me, it's often a secondary consideration, actually. So to the extent that beauty and simplicity are connected, which I do think they are, simplicity is actually the more powerful, practical test. Here's what I mean. If I have a student and we're working on some problem, say for that person's PhD thesis or something, usually it involves thinking about something unknown that we don't know how to solve, that's at the edge of what mathematicians, or in my case, applied mathematicians, meaning mathematicians who are outward looking and direct their math at nature or technology, not inward at math itself. We're trying to solve some problem and we don't know how to do it. And where simplicity is helpful is that if you can simplify the problem, make the problem easier in some way, such that you still don't know how to solve it, but you have more hope of solving it because it's easier, that's often a good heuristic, a good strategy to use to make progress. Rather than just being stuck and pounding your head on the hard problem, find a simpler problem that you also don't know how to solve. Now, you could say that's cheating. You're changing the problem. But look, there's no such thing as cheating. You can do anything you want. We have a lot of freedom in science and math. Not ultimate freedom. We want to compare to the truth or to compare to reality. But still, to get there, you don't have to get there in one step. And so I use simplicity very often as a strategy. Keep simplifying the problem actually fairly ruthlessly till it's minimal, till it's the simplest problem that contains the nugget of the difficulty, the essential difficulty. And that's actually my taste in math. Different people have different tastes, but my own taste is I like to do the simplest thing that contains the essential difficulty. And so I like to sometimes compare it to Impressionism in art, that if you look at an Impressionist painting, it's not photorealistic. Think of, I don't know, Seurat with the bathers on the beach or whatever it is. It's all these different dots. If you look at it up close, it's a lot of dots. You say there's nothing there but dots. But somehow, between the colors and the arrangements of the dots, he captures something essential. And I sort of like doing that. I like stripping down my paintings or my math to its minimal form and ignore certain other aspects that I don't consider essential.
That's really interesting. What you just said, I think, applies exactly in the same way to how physicists approach problems, especially theoretical physicists.
Absolutely.
But I never thought about it in the context of pure mathematics. So what's the relationship there? I mean, are you basically just talking about the application to real-world problems, which then I think is essentially like physics? Or is this also something that's important within mathematics?
It is. It's important in both. It is important in mathematics. So let's see if I can think of an example of this from my own work. Sure. Yeah, I can think of a case. There was a problem. You mentioned in the introduction that I had worked with my student, Duncan Watts, years ago about small worlds and how it is that we could all be just a few degrees of separation apart in the social network. And we started thinking also about, how is it the case that so many systems in nature, not just social networks of people, but say neurons in the brain. I had neuroscience friends who used to say every neuron is just a few synapses away from every other neuron, even though there are 100 billion neurons or something in the human brain. So how could we only be 5 or 6 synapses away in something of that size? Also keeping in mind that each neuron makes on the order of like 10 to the 4th synapses. So it's not like you're connecting to a large fraction of the whole 10 to the 11th neurons in the brain. It's only 10 to the 4th. It's nothing. It's less than 1 part in a million. Mm-hmm. So how could it really be true? And anyway, so we were interested in these large interconnected systems with this kind of small world property that everything is surprisingly close to everything else. And in the math problem that was related to that, we wanted to know, would small world networks of this type have an amazing ability to synchronize themselves? Because you have all these short pathways that is like very rapid communication is possible in a small world. This is what we're seeing with the pandemic, right? That everybody is only a few hops from Wuhan, China. But anyway, back to what does this have to do with simplicity and how do mathematicians use this? When we were trying to think about how these networks in a neurological sense might be able to get themselves in sync very efficiently, despite being gigantic, we started to realize that the problem was already extremely difficult to think about, even if we didn't have a network as complicated as the network of neural connectivity of the human brain. So we would look at much simpler organisms like, say, C. elegans, the roundworm, whose nervous system was completely mapped. Every neuron, every gap junction, every synapse, only a few hundred neurons there, 300 or so. Still, that problem was too hard for our math. We couldn't analyze synchronization of the C. elegans network. There are too many different types of neurons, too many different types of interconnections. So in the end, we boil it down to trying to think about, can we study something like a ring, just a bunch of dots arranged in a perfect circle, where each one is connected, let's say, to the same number of neighbors on either side. So like an extremely symmetrical shape, using your concept there, Martin, of symmetry. What can we say about properties of synchronization of a ring of oscillators with perfect symmetry? If we can't solve that problem, we have no hope of solving C. elegans and certainly no hope of solving the human brain. So that's what I mean.
Perfect sense.
That we would keep boiling and boiling until we got to the simplest problem we couldn't solve. And that gave us a lot of mileage. The only thing, though, and this should be emphasized for honesty's sake, that now we're solving a problem that we don't really care about. Like what happened to C. elegans or what happened to the human brain? So this is a constant tension when you take this approach to science or math of relentless simplification. You may be working in a realm that becomes more solvable, but it also becomes less and less relevant.
Didn't Einstein say that everything should be as simple as possible, but no simpler?
Yes, exactly. Well, then that's where there's taste. I mean, there's a lot of taste involved in deciding what does that mean exactly, which is too simple and which is simple, just exactly the right level of simplicity.
Maybe that's part of the talent of good scientists, to have the right taste for the right level of simplicity.
Mm-hmm. It is, but I think it's very subjective. This is something we don't normally talk about in science, the subjective aspect, because we want to think we're doing objective work. But there is a subjectivity in deciding, do you want to study the real system? I mean, there are people who really do want to simulate the connectome of the human brain. There's big brain projects or whatever they call them, where people are using supercomputers and they want to do realistic models of the neurons and stuff. And those people are good scientists. They just have different taste than my taste. And I would say I take an extreme minimalism perspective on this, which honestly is a little bit of a no-no in applied math. The culture of applied math says the criteria for what is good applied math is, are we making a genuine contribution to science? Like say, for instance, I worked on fireflies and how fireflies get in sync. My models of fireflies are not realistic, and I know that they're not. So what they tell me doesn't tell me much about real fireflies. And so some mathematicians would say, well, you're not doing genuine applied math. You're just fooling around. Like you've left out important essentials. But the truth is, I don't really, in my heart of heart, care about fireflies. What I really care about is this phenomenon of a group of individuals spontaneously synchronizing. I like that problem, and I don't really care that it's fireflies. I use nature as an inspiration for math, whereas most applied mathematicians use math as a tool to study nature.
Yeah, I think it shows that in your heart, you're really a mathematician.
I think so. But then I'm sort of neither fish nor fowl, because I also don't prove theorems the way that a so-called real mathematician does. I'm willing to accept evidence from computer simulations, from physical intuition. Those are big no-nos for pure mathematicians. So I kind of live in the cracks. I like interstitial work, actually.
But Steve, could I suggest an alternative hypothesis to what you really are? Maybe you're not so much not an applied, but actually a more pure mathematician, but rather you like general problems. I think the reason why you like the firefly model is because it's actually applicative to many things, like an audience clapping, like the London Bridge shaking. And so you think if you solve just one case of it, you will have solved a whole class of problems.
Well, you've done a very excellent job of making the case. That's exactly the positive case. But the counter argument is, yes, it's general and it's attractive for that reason. But have we abstracted too much? Have we taken out so much of what really matters, let's say, on the Millennium Bridge in London, that we're just blowing smoke? The math that we're doing doesn't apply anymore. There was a recent article in Nature Communications just in the past few months saying exactly that. They refer to the myth of the Millennium Bridge, that the work that we did, we, my collaborators and I, when we wrote a paper in 2005 about the Millennium Bridge and why it wobbled on its opening day in 2000, that all of that has been a pernicious myth that has set the field back for the past 15 years. Because although it was a beautiful thing we did, it's just wrong. It just doesn't have to do with what really happened on the Millennium Bridge. And honestly, I think they're right. I think they are probably right, that empirically what we found is not the operative mechanism for the Millennium Bridge. So was that a harmful thing that we did? I don't know.
Maybe you were wrong in a very interesting way. And then
yeah, I think we were wrong in an interesting way. I think it's been productive for the field. I actually don't mind being wrong. You know, the goal is to get to the truth as a society, as a group of scientists. And in science, we talk about hypothesis testing, and it's important to make a hypothesis that's refutable, that's falsifiable. And so we really stuck our neck out. We said, this is what's happening on the Millennium Bridge. And if this is what's happening, these would be the consequences. And it's testable. And in fact, it's demonstrably wrong, as it turns out. I mean, time has shown that what we proposed doesn't work. But it was interesting. We didn't do a waffly thing. We really did stick our neck out and unfortunately got our head chopped off.
Yeah.
But okay.
I mean that's how science works, right? You have to come up with a hypothesis, and in the end, if it's tested, it might come out wrong. But if you have no hypothesis, there's nothing to test. Then you're not going to make any progress.
So I feel like it was okay. I felt like we played by the rules. We weren't lying. We said what we were doing.
Right.
Yeah.
That's science.
Totally. I must say, I'm fascinated by this idea that it's a matter of personal taste, and I guess also of choice in a specific situation, how much you simplify a problem, how much you coarse grain it, if you want, right? How much you leave out of the problem. And I think that's a very useful way to think about problems in science that you're faced with, to just consciously think about how simple can I make this, and how much do I think does it then still resemble reality?
I completely agree. And I think this is something that any practitioner in any part of science or math will recognize. I think let's take the case in neuroscience again. There are people who want to study the whole brain. They may be psychiatrists. They want actually not just the brain, they want the brain inside the patient. Other people would say, oh, that's ridiculously hard. I can't possibly understand that. I need to study neural networks. I want an ensemble of, so they will work on the lobster stomatogastric ganglion, which is this well-characterized small network of neurons. They know every ion channel in those neurons, and they can measure all the currents and conductances and everything. Now, you're not doing anything of great interest. Nobody cares about the lobster stomatogastric ganglion per se, but it's a model system. This is the concept always used in biology and in physics and in math. There are model systems that are more tractable than the real thing. And then, of course, other people who have more of a penchant for minimalism would say, oh, no, I don't want to look at a whole network. That's too complicated. I want to study one neuron. And then someone else below them says, are you nuts? A neuron is a complex system. I want to study one channel, one ion channel. I want to understand the conductance properties of this one potassium channel. So all of them are doing worthwhile science. And I think we have to be honest with ourselves. Where does our own comfort or happiness lie? Because we get to live one life as far as we know. So I want to live in a place of extreme simplicity. That's what makes me happy. Or as Itai kindly put it, it does have this advantage of generality. I also love all of science. I want to do something that relates to physics and chemistry and biology and astronomy and math. I like flying around over the landscape of all of these fields. But when it comes to getting down on my knees in the muck, I'm not that kind of scientist. I don't want to be doing that kind of detailed work, but I love it that other people do.
We noted that Sparks of Genius by Robert and Michelle Ruth-Bernstein is a book that you recommend. And I love that book too.
Oh, good.
Yeah, I really enjoyed it. And I'm wondering if you could tell us why you recommend that.
There are many things I like about the book. It's, first of all, very well written. It's got good stories of real scientists from many different fields, not just scientists, artists too. So it's very interdisciplinary by nature, which appeals to me. It's historical, which I like. I love hearing stories of great thinkers and creators. So it's concrete. It has many examples. It's not a wafty philosophical treat, although of course I like philosophy too, but it's very action oriented. Like if you want to be a better scientist or a better creative person, maybe in the business world or as a lawyer or whatever you do, this book gives you thinking tools that great geniuses have used. For instance, the importance of playfulness. Playfulness, a lot of people think play is a waste of time. Or why are you playing around? Why aren't you getting serious? Right. Well, those are not creative people. Anyone who's creative knows that play is a very important component of creativity. And I think the Ruth-Bernsteins give this example of the bacteriologist, maybe it's Alexander Fleming.
Fleming, yeah. And how he discovered
right?
Penicillin. Right, yeah. Didn't he make art? He made art.
That was the thing. He would use bacteria to paint. He was painting with his specimens. You'd say that's...
And that's how we got antibiotics.
Well, what's really the story? So you'll have to read the book to see the story, but it's often portrayed as some kind of serendipitous discovery. But the book shows that, no, that's not true. Not exactly. Fleming would paint with bacteria partly to develop his technique, his lab technique, sort of like when musicians play around. They get better at music. So his technical skills got better, but it also gave him associations in his mind that were not exactly logical. He was forming connections that were beyond logic, from body feelings, from maybe the smell of the bacteria. I forget the details.
The color, right? That was the color of the...
Okay, yeah. So there's a lot to being creative than just logic, a lot more than pure logic. And so play opens you up to all those kinds of things. Plus, it's fun. It helps increase your motivation, keeps you wanting to go back to the lab each day. So anyway, they tell rich stories like this of many different people in different fields.
So we now talked a bit about the book Sparks of Genius, but of course, at least a little bit, we would love to also talk about your amazing book, Infinite Powers. So in the book, you cite from a letter of the ancient Greek mathematician Archimedes to his friend, where he provides insight into his creative method. We loved that story. Can you retell it to our listeners and tell them a little bit about what it means to you?
Sure. Yes, it's a story of ancient times. We're going back now to about 250 BC in the island of Sicily, a place called Syracuse, where Archimedes is a Greek mathematician who is really one of the greatest thinkers of ancient times. He was very interested in properties of curved shapes of all kinds, circles, spheres, parabolas. Those were the frontier of math in his day. People knew a lot about shapes that were built out of straight lines like cubes and triangles and that kind of thing. Anything with flat faces or straight edges was relatively easy to understand, but curves were the great unknown. How do you quantify the area inside a circle or the area under a parabola? These are the kinds of things that Archimedes figured out, and this is 2,000 years before the invention of calculus. Essentially, he figured out calculus in some ancient form that was able to cope with problems of curvature. So anyway, one of the ways that he did this was by Some people will know Archimedes' name because of his principle of buoyancy, that as I memorized it in high school, a body immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced. So I still remember that exact formulation, but the basic idea is when you sit down in the bath, you feel the water pushing up on you, and it's pushing up with a force equal to the amount of water that your body has pushed aside. Anyway, so this is used in analyzing stability of ships and figuring out which things will float and which things will sink. And so Archimedes was interested in floating bodies and the mechanics of them. But he used an analogy between floating bodies and the force on them to solve problems he cared about, like what's the volume of a sphere or what's the surface area of a sphere. He also did work in mechanics where he came up with the principle of the lever, which, is like when we're on a seesaw in the park, the heavy child can sit closer to the fulcrum and the lighter child sits farther away, and then the two can balance. So if the ratios of their weights are in the same ratio as their distances from the fulcrum, or maybe it's the inverse ratio. Anyway, here's the crazy thing. To figure out properties of curved shapes, he imagined them as palpable weights, like things with mass, and he imagined weighing them in his mind against shapes whose volume or area he already knew. So he calculated the volume of a sphere by thinking of it as a sphere of substance, and then imagining doing certain mechanical experiments with weighing it. It's too much to try to explain in a podcast, but the gist of it is that he had this very interesting intuition comparing a mechanical method for weighing objects with a geometrical method for figuring out their volume, which, as I say, was an unknown thing at the time. So he starts explaining this method in a letter to Eratosthenes, who is another great mathematician working in Alexandria, Egypt. And so he explains to Eratosthenes his mechanical method for doing geometry. But this is the part that I think is so memorable, that he says that this method only gives some kind of indication of the truth. It's not a proof. He doesn't consider it rigorous. He doesn't really totally trust it, but it leads him to right answers, like it works. But he's not exactly sure how to justify it or whether it should be trusted. But he says in the letter, it's much easier to prove something is true once you already know the answer. And so the method gives him intuition. It's a guide to what's true, even if it's not a reliable guide to a proof. And once he knows what the truth is, he can then use geometry to figure out a proof. So he solves problems about volumes two different ways. First, he discovers them with the method of weighing in his mind, and then he proves them with geometry that he invents. And so I just think it's a really cool, honest, inspiring story. It's actually very fitting for your podcast, which may be why you want to talk about it. That what we do in science at night, like the method is what he does at night, and the geometry proof is what he does in the day.
Yeah, exactly.
And what's really nice about it also is, we have to go back over 2,000 years to find a mathematician who can be very open and honest about his method. Because most of the time, all we see is the final product. What students learn in school are the proofs, and maybe we don't do as good of a job. And it's a point that you make in the book too, that we don't do as good of a job of teaching the intuition.
Yes, something strange has happened to mathematical communication since the time of Archimedes. I'm not sure exactly when. I sort of think it's sometime in the 1800s. It ties into our earlier conversation about aesthetics. Sometime in the 1800s, an aesthetic came to be widely accepted that being concise was a high form of mathematical elegance. Don't use more words or more explanation than necessary, including, this is really sick, don't even draw diagrams, because diagrams can sometimes lead you astray. Sometimes you'll prove things based on the picture that aren't logically correct because you're deceived by the picture. So there came to be a move to expunge geometry or visual representation from the teaching and communication of math. And even in the 20th century, there were people who saw that as an aesthetic virtue, to remove the diagrams and use as few words as possible. And I want to use the word perverted. I think this is a really perverted, freakish, wrong, twisted view of communication. While it might be elegant in some sense, it ignores certain realities of human psychology, that a lot of us like visuals and understand things better with intuition and visuals. I mean, Archimedes understood this. Intuition first, rigor second.
Right.
You need
Yeah.
both. You need
Yeah.
both. And so I think it's really a corruption of the whole process to only show the rigor and not show the pathway leading to the understanding. I do feel like science is a sociological enterprise, that a person doing science or math in their basement that never tells the world about it, they might have made nice discoveries, but I don't think it qualifies as science, because science is a social enterprise. It requires communication with other human beings. And if you don't do that part, you're not doing science in my book. With my grad students, I'll sometimes hear them say things like, I love doing the work, but I can't stand writing it up. That part doesn't feel like I want to do the next problem. And I understand that impulse. It's commendable in a way to love your craft. But I think the craft is multifaceted. There's the discovery, but there's also the communication. And if you're not doing both to the best of your ability, I don't think you're really living up to your potential as a scientist or your responsibility as a member of the community of scientists. And I think it's underestimated how valuable that side of things is. I've made a lot of effort to be the best writer I can be and give coherent talks and all, and even communicating with the public, trying to do public outreach. That stuff, although it takes time, I actually think it's very useful for those who care about career advancement. Like if you can write a grant proposal in a way that the referees will understand it, I think you have more chance of getting better funding. You can do more work of the type that people think is real science. I guess what I'm saying is don't sell the soft part of science short. That part, the communication side, is something that every hard-boiled scientist should care about. It really will bring in more money, more recognition. You mentioned about being a member of various learned societies, getting elected to this or that. I think that's probably, if I'm being honest, more because my communication is strong than that my technique scientifically is strong. I think there are much stronger mathematicians than I am who are underappreciated because they haven't communicated very well what they actually did.
Yeah. I mean, if you make great discoveries, but you're not able to communicate them well to your fellow scientists, they might be overlooked, right?
Mm-hmm. They can be. So, and that's a pity, but I don't have that much sympathy for people who haven't made the effort. I mean, if we're trying our best, okay, then I do have some sympathy that because life can be unfair and so can science. But for people who don't try, I really wish they would. I actually feel like science and math have a distribution problem more than a production problem, to use language of economics. That there are a lot of great ideas being produced and great discoveries being made, but we don't have a great distribution mechanism for helping other scientists appreciate what's been found in adjacent disciplines, or helping the public speak about translational medicine or technology transfer. These are all distribution problems. How do you get the great ideas to a place where they can have real impact? I don't think we need more scientists making more discoveries. We need better distribution of existing discovery. We need both.
No, totally. So, Stephen, we talked a lot about creativity now. And Itai and I were actually wondering if perhaps this episode of the podcast should be called Night Mathematics rather than Night Science. Do you think there's a difference between creativity in mathematics and in the empirical sciences?
I don't know what to say to that. My instinct is to not make a big distinction. The argument in favor of making a distinction is that pure mathematics doesn't rely on reality, doesn't need reality. It also is the one part of human mental activity where we can have absolute proof, whereas everything in science is always provisional and relies on experimentation and observation. And I mean, you know all these concepts, but I don't know if I really believe all of that so much. I mean, yes, I can understand those arguments and there's some truth to them. But the fact that both science and math are being done by people and we're fallible, like we don't really have absolute proof, much as we would like to believe that we do. Even Euclid's proofs from 300 BC, there are gaps in those proofs. They're not exactly wrong. He didn't say anything wrong, but there are points of rigor that are missing. So some historians of math have made the point that, Euclid spent a lot of effort on talking about constructing shapes. Like there's all this talk about straight edge and compass constructions. You draw circles with the compass, you draw straight lines with the straight edge, and Euclid spends a lot of effort making proofs of how you would construct a perpendicular bisector of a line segment or whatever, how to construct an equilateral triangle given one side of it. Why this emphasis on construction? Some people say that, let me just say what I think is an interesting argument that a historian named Victor Blasio has made, which is that he says the reason Euclid cares about construction is because for him, geometry is partly empirical. It's not pure math the way we think of it today. He's actually going to construct an equilateral triangle with a literal straight edge and compass, knowing that in the real world, those are imperfect. You can't draw a perfect circle. Any line has a thickness, etc. But still, it gives him a guide to what would happen if he had a perfect straight edge and a perfectly thin line. Like, in other words, he makes shapes so that he can test what he thinks he's gotten by logic. He can check it against the physical construction. And so I think that that's emblematic of how math really operates in the real world. That the mathematicians, even though we like to say we're different from scientists, we're not that different. We also have experiments. We also have constructions and examples and empirical things. In the end, we try to hide them or get rid of that scaffolding and say we're in the world of pure thought. But I think as a matter of practice, we actually behave very much like scientists. So no, I would not make a big distinction. And so for that reason, I also don't think mathematical creativity and scientific creativity are fundamentally different. I think they're fundamentally the same.
Great. So the name stays. It's night science after all, Martin.
Yeah. I like the word science. So for me, in fact, I don't like the phrase STEM. I would get rid of that. And then, some people go in the opposite direction. They want to call it STEAM. They want to add arts, STEAM. And then I think, oh, come on. How about just like all of school is valuable and so is all of life. You can learn from everything. And why are we making these artificial distinctions into STA? And, come on. It's just open your mind.
I think that's the perfect phrase to end today's podcast.
Absolutely. Steve, thank you so much. This was so enjoyable.
Oh, thanks, Martin and Itai. It was a real pleasure. You guys were great to talk to. Thanks for having me.
Thank you.